Hi everyone. In the last video we went through an example where we used Gauss's law to find the charge that's enclosed within a surface given the electric field. But I should mention that even though these types of problems will often come up on tests and AP exams and stuff like that, the more common type of problem and often the more practical problem is to actually use Gauss's law and some known charge distribution to figure out what the electric field is going to be as a function of position. So that's the more useful situation in general. Now, in today's video, we're actually going to take a mathematical aside and examine Gauss's law and really how it comes about using something in multivariable calculus. Though what we're really going to be doing is we're going to motivate a very important theorem in multivariable calculus. So it's math that you don't need to know, which is why I'm containing it just within this video, aside from the rest of the videos in this unit, though it is going to be part of the playlist. So it will help you to understand why Gauss's law is true, and for those of you who are currently taking a multivariable calculus class, it will also enhance some of your skills in that, or at least give you a better conceptual understanding of some of what goes on. So let's consider a source charge right here. So you have some bunch of charge, and we're trying to figure out what is going on with the electric field at a number of points here. And you'll notice that within this cone of charge, as you keep going out, you still have the same number of electric field lines. It's just that as you go out, more and more surface is required in order to contain these field lines. So what really matters, though, is how many field lines diverge from the source. It's independent of distance, in other words, in this situation. So there's actually a mathematical way of measuring how a vector field diverges from a surface. It's called the divergence, and it's given by this expression. The divergence vector dotted with the electric field vector. Now the divergence vector is actually a vector operator, and it's often called delt or grad or nabla, though I should mention that in the most recent version of this PowerPoint I was actually able to edit it so that it's no longer italicized, because it shouldn't be italicized. So now I'm just going to say that now I have edited it, disappear warning, and lo and behold, the warning disappeared. So again, it tells you, it just denotes divergence when you're taking a dot product of something following it. Now, this only works if the thing following it is actually a vector field, that is. So the whole idea of this upside down triangle, this nabla, is that it's a vector itself. It's a vector operator, and it's telling you to, at least if you're in rectangular coordinates, add together the partial derivatives with respect to each of your variables times the unit vector in that case. In other words, nabla is literally partial xi plus partial y j plus partial z k. But if you're making a dot product of E vector, which is E sub xi plus E sub yj plus E sub zk, then after applying the distributive property and the fact that I dot j is 0 and I dot k is 0, etc., and j dot k is 0, then the only things that are left over just become partial x of E sub x plus partial y of E sub y plus partial z of E sub z. Where these are partial derivatives, you're taking a derivative only with respect to the variable that is indicated. So in any case, that's what the divergence of this electric field vector is, or any vector that happens to be called E vector. So there we go. Physicists often use cylindrical or spherical coordinates, and in those cases the divergences end up looking a bit different, but still you'll be able to deal with it. In this case, I'm just showing you what it is in the radial direction, because that's what we're often going to be dealing with. But there is angular dependence, which is nastier. The good news is that when you're applying Gauss's law is only going to work if there isn't angular dependence. So in any case, the divergence is something that can be measured at a point. That's the whole point of this. So if there's no source of charge at that point, then the divergence is going to be 0. But the more dense the charge distribution at that point, the more electric field lines are going to be created at that point, and thus the more electric field lines are going to diverge from that point. So this relationship between the amount of electric field divergence and the density of the charge can be stated in this equation. The divergence of the electric field is equal to the charge density there, the volume charge density, divided by epsilon naught. That enclosed charge thing divided by epsilon naught, that looks kind of familiar. In fact, this is the true form of Gauss's law. However, in a lot of situations, especially in high school AP Physics C, Electricity and Magnetism, or 200 level university physics, this isn't a very useful form of Gauss's law to use for calculations. So how is this related to the form that we actually use? Well, notice that if we were to take a volume integral of the right side, after all, this is a volume charge density, if we were to take a volume integral over our entire charge distribution, then you would get the total enclosed charge, at least up to a factor, that epsilon naught factor. In other words, the enclosed charge is equal to the sum of all of the little bitty charges that are enclosed. So I use this triple integral sign to denote that this is actually integral over a volume, even though when we use Gauss's law in future discussions, we're generally just going to be going over one dimension because there will be no angular dependence. There will only be a radial dependence. So we're just going to take an integral with respect to radius when we employ this. So what does this mean? Well, since whatever you do to one side has got to be equal to whatever you do to the other side, if you take the triple integral of both sides, then the triple integral of the left side is equal to the enclosed charge over epsilon naught. Oh, that's starting to look kind of familiar. That's kind of interesting. But wait, there's more. We know that the enclosed charge is equal to that surface integral of E vector dot dA vector. That's kind of something to keep in mind as we're going with this. So on the left side the far left side of this equation, electric field lines don't disappear or pop up unless there is a negative or positive charge. So in other words, whatever is created within a volume must be accounted for at the surface. That's actually really cool. In fact, that's so cool that it is a mathematical theorem. In fact, it's called the divergence theorem in most multivariable calculus books, but it's also sometimes called Gauss's theorem. In fact, it's a general rule that the triple integral, the volume integral of any divergence, is always equal to the surface integral of the dot product of the whatever vector field you took the divergence of dotted with the area. In other words, whatever's going on inside can be accounted for by what's going on at the surface. So there we go. That's what we had for our Gauss's law, and that's the Gauss's law that we are used to. So note, I did not derive Gauss's law. If you note that, or at least I did not derive the divergence theorem. Note that right in here, I said that, hey, this is equal to the integral of the electric field vector dot dA vector. So we're kind of using that a little bit as an assumption. But remember, in the previous video, we motivated this fact by showing that it has to be true for a point charge, and then hand-waving into existence the fact that if you have a bunch of point charges, it's going to remain true because the electric flux through surfaces that are in between little spheres surrounding each of your point charges is always going to be 0. because any field line in is going to be canceled by a field line out if there's no enclosed charge. So even though, yeah, we didn't derive the divergence theorem, but we noted the fact that this right side is true because of our previous discussion. And therefore we realize, hey, with this electric field, it ends up actually working out in the case of the electric field. In fact, it didn't have to be an electric field. It could have been any vector field, which you might as well just call F for vector field. And that is the divergence theorem, also known as Gauss's theorem. But overall, this is the result for us. And by Gauss's theorem, that is what we call Gauss's law, this is what is true for us, at least in the form that we are often going to use it. So that is the end of our mathematical diversion, where we have kind of motivated the form of Gauss's law that we use by starting from a fundamental form, which might, the fact that the divergence of the electric field at any point is equal to the charge density at that point divided by epsilon naught. The fact that it's proportional to the charge density at that point should be intuitively obvious. The fact that the proportionality constant is 1 over epsilon naught, you could say, is kind of a result of our previous analysis of imagining a point charge and a sphere around the point charge, and then just taking that sphere to have a radius arbitrarily close to 0, giving you simply a volume charge density. So in the next discussions, we will come back to our normal form of Gauss's law and start using that for calculations, starting off with situations involving spherical symmetry. I'll see you all then, and thank you for watching.